So in the last segment, we saw the randomized algorithm Quicksort, at least a brief description of it. In this segment, we will actually analyze it thoroughly, and we'll also look at a problem related to sorting called selection, and look at a randomized algorithm for selection as well. So let's recall how Quicksort works. The idea is to choose an element in the array at random, to partition the other elements in the array into those that are smaller than the chosen element and those that are larger, and recursively sort the left and right sides. Here's the pseudocode, and here's the algorithm working on an example array. So let's compare Quicksort to merge sort, at least in terms of the top level logic. So they're both divide and conquer algorithms. Quicksort first partitions the array and then recursively sorts. Quicksort can be done in no extra space, and now we'll analyze the runtimes. The first, what does Quicksort do? It picks a random element of the array and partitions all the other elements. How long does that take? Well, it has to compare every other element to the chosen element, which is called the pivot, by the way, sometimes. So this takes order n comparisons. Every element requires one comparison with the pivot, that's order n. Now it has to recursively sort the left and right sides of the array. And the running time really depends on how that split works out. So what are the sizes of those two arrays, the left and right sides of the pivot? Well, let's say they're k and n minus k minus 1 for some value of k. So if k is 1, for example, there's one element that's smaller and n minus 2 elements that are larger than the chosen pivot. Okay, so k and n minus k minus 1 are the two sides. So T of n, the time it takes to sort n elements, would be T of k, the time it takes to sort the k smaller elements, plus T of n minus k minus 1, the time it takes to sort the larger elements, plus order n, which is the time it takes to divide every element, to partition all the elements. So the worst case, the worst thing that Quicksort can do is that you get a really bad partition. You pick a pivot that's so small that the left side is empty. There are no elements smaller than the pivot, and all the elements are larger. In this case, you would get T of n equals basically the empty set, T of 1, plus the time it takes to sort the n minus 1 elements that are larger, plus the time it took you to do the partition, which is n steps. And if you look at the analysis of this, it works out to the same as insertion sort, and it's T of order n squared. On the other hand, the best case for Quicksort would be that every time you pick the pivot, you get this perfect split into equal size sets of smaller and larger elements. So if this happens, both sides have about n over 2 elements in them, and then T of n would be T of n over 2 to sort the smaller elements, T of n over 2 to sort the larger elements, and n to do the partition again. And this is exactly like merge sort, and it's order n log n. So you have the worst case and the best case that are quite different from each other. So which is the real thing? How does Quicksort really behave? So maybe what we want to understand is, how does the algorithm perform in expectation? What's the average over all the coin tosses of the algorithm of the running time? So let's look at the analysis of Quicksort. The recurrence for Quicksort for its expected behavior, it has to consider that the pivot could be the ith smallest element for every possible value of I. So if you take the pivot to be the ith smallest elements, the left half would contain I elements, say the I plus 1 smallest element, the left half contains I elements, and the larger half contains n minus I elements approximately. So then T of n is going to be the time it takes to solve the problem on I elements, the smaller elements, and n minus I elements, the larger elements, plus the time it takes to partition. Now all of that is if you choose the pivot as the ith smallest element, but of course it could be any one of the elements. The pivot is chosen completely at random, so we have to average over every possible choice of I. So this is why it's 1 over n, that's the probability for any particular choice of I, and the choices of I range from I equals 1 to I equals n. So that's a messy recurrence relation to analyze, and we don't want to get into that. So we want to see, can we find a better way to analyze Quicksort? And the idea is going to be to use random variables, linearity of expectation, all those great concepts that you saw in the last segment. So some of the basic points I want to make: Quicksort never compares two elements twice with each other. It compares two elements maybe once, but never again, because it knows the order between them after it's compared them once. The other thing to note is that the only comparisons that Quicksort makes are comparisons between an element and a pivot. It never compares two elements if neither of them is the pivot at this point. Okay, so the only comparisons are between elements and pivots. So basically, after an element is compared to the partitioning element, the pivot element, it will never be compared to that element again. So let's denote the kth smallest element in the array as ek. Let x be the total number of comparisons performed by Quicksort. And let's let these indicator random variables, create these indicator random variables xij, which xij is going to be 1 if the ith smallest element and the jth smallest element are compared to each other. And it's going to be 0 if they are not compared to each other. So if ei and ej are compared, xij is 1. Otherwise 0. So since xij is just counting whether the element I is compared to the element j, if we sum over every possible pair I and j, we'll get the total number of comparisons performed by Quicksort. So x is the sum over all, basically these two sums are running over every possible combination of I and j exactly once and counting whether they are compared to each other or not. So we want the expectation of x, and we can break it down by linearity of expectation to calculating the expectations of the xij's. So expectation of x equals the expectation of sum over I of the xij, sum over I and sum over j of the xij's, which is just the sum of these expectations of xij's. Now the expectation of an indicator random variable is particularly easy because the indicator random variable takes on only two values, 1 and 0. And we don't care about the 0 value because the probability of it taking on the 0 value is multiplied by 0. So this is going away. So all we need to know is this: the probability that xij equal to 1 is in fact equal to the expectation of xij. So expectation of xij equals the probability that xij equals 1. So all we need to know is what is the probability that the ith smallest element is compared to the jth smallest element. If we figure this out, we will have a handle on analyzing the expected number of comparisons performed by Quicksort. So we'll analyze this with random variables. What is the probability that ei and ej are compared? So ei and ej will be compared if either is selected as a pivot, and ei and ej will not be compared if something in between is selected as a pivot. So let me explain that with a figure. So imagine that all the elements in sorted order like on a line like this. ei is this element here, ej is this element here, and we want to know what's the probability that they're compared. So you're choosing pivots. If we ever choose a pivot in between ei and ej, if that is your pivot element, what's going to happen when we partition based on this pivot? Ei is going to go off into the left set, and ej is going to go off into the right set, and they will never be compared again. So any pivot that's chosen strictly between ei and ej will result in ei and ej not being compared. If a pivot is chosen to the left of ei, then both ei and ej will lie in the same set. So the question of whether they're going to be compared will be decided in the future. This is not affecting whether they're going to be compared or not. Similarly, if we choose a pivot on the right side of ej, then again the question of whether they will be compared is postponed to a future decision. So to summarize, ei and ej will definitely not be compared if we choose a pivot strictly between them, and they will definitely be compared if either ei or ej is chosen as a pivot. The number of elements that would cause ei and ej not to be compared is just the set of elements which cause ei and ej not to be compared is just ei plus 1 through ej minus 1. So that the probability that that ei and ej are compared is just 2 divided by j minus I plus 1. which is basically, again, why is that? Because you have a line here, here's I, here's j. So in between there are a total of j minus I plus 1 elements. And out of all the possible j minus I plus 1 choices, exactly 2 choices, namely I and j, will cause EI and EJ to be compared. So the probability that I and j are compared is just 2 divided by j minus I plus 1, 2 divided by this. And therefore, the expectation of xij is also 2 divided by j minus I plus 1. And the expectation of x is just the sum over I ranging from 1 to n minus 1 and j ranging from I plus 1 to n of this quantity. And you can work out this sum basically by using some algebraic manipulation and see that this is less than or equal to 2n log n, which is order n log n. So quicksort in expectation has the same behavior as merge sort. It's a very practical algorithm. It works very fast in practice. And it's actually one of the popular algorithms that are actually used for sorting. So now let's talk about an entirely different problem from sorting, but somewhat related to sorting. It's the problem of selection. What is selection? You're given an array of elements. Again, they're not sorted. And you want to pick the kth smallest element in the array. So maybe you want to pick the 100th smallest element in an array of 10,000 numbers. So how do we do that? How do you pick the 100th smallest element in an array? Well, one way you could do that is to sort the array, either by quicksort or by merge sort or any other sorting algorithm. Once you've sorted the array, then finding the kth smallest element is easy. It's just the element at location k minus 1. Remember that our arrays are indexed starting at 0, so that the kth smallest element is at location k minus 1. The time required to do this is the time required to sort, which is n log n. And the question is, do we really need n log n to pick the kth smallest element, or can we do better? So the idea of quick select is to follow quicksort in some sense. That is, quick select will partition the array using a randomly chosen pivot. But unlike quicksort, which after it's partitioned the array, it has to sort both halves, in quick select, once we've partitioned the array, we know that the element we are looking for lies on one side or the other, and we only have to recurse on that side. So as an example, so we want to find the 6th smallest element in the array given here. We choose the pivot 3, and we divide the array as shown here into the elements that are smaller than 3 and the elements that are larger than 3. So this means there are only 3 elements smaller than 3. This means 3 itself is the 4th smallest element. 4th smallest, right? So 3 itself is the 4th smallest element. And we want the 6th smallest. So we know we need to delve into the larger set. That's where the 6th smallest is going to be. And it's going to be the 2nd smallest element out of the larger set. Why? Because we originally wanted the 6th smallest. We've got 3 that are smaller than the pivot, and then the pivot itself is the 4th. So we need to count 2 more to get the 6th smallest. So we're looking for the 2nd smallest element on the larger side. And we repeat. We choose a pivot there, and we partition. And we find that the smaller set now has 3 elements in it. So we want the 2nd smallest element still in the smaller set. And we repeat, and we get the answer 5 in the end. And the pseudocode for quick select is given here. How do we analyze this? So we can use an analysis very similar to quicksort. And what will happen is that because we throw away 1/2 of a partition every time we do a partition, you will actually find that there's a smaller probability that elements are likely to be compared or to be compared. So we'll use the analysis using random variables. As before, let the kth smallest element in the array be denoted as EK. And we can ask ourselves, what is the probability that EI and EJ are compared when selecting EK? Okay. So we're looking for the element EK, the kth smallest element, and we're asking what is the probability that EI and EJ are compared. So there are 3 cases depending on the relative order of K, I, and J. Let's always assume that I is less than j, because that's without loss of generality. So case 1 is that the element we're looking for is smaller than ei or ej. So it's the smallest, k is the smallest index, I and then j. So when would we compare ei and ej? Let's consider various pivot choices. If we choose a pivot here, let's say, what would happen? We would split into the elements that are smaller than the pivot and the elements that are larger. ei and ej are both larger, so they would go into this bigger set. But we would realize that we want to recurse on the smaller set. So we would realize that we want to recurse on the smaller set, so we would not compare ei and ej in this case. So that's one case. Now the case 2 is where I is less than k is less than j. In this case, no matter if we pick a pivot anywhere in the range ei to ej, that's not ei or ej, we won't compare them. We only compare them if the pivot chosen is exactly ei or ej. So the probability that ei and ej are compared is 2 over j minus I plus 1, exactly as for quicksort. Case 3 is when k is to the right, and this is exactly like case 1. Okay? And the runtime of Quickselect is exactly like quicksort. The total number of comparisons, it works out to be linear. So basically we expect to do only order n comparisons for Quickselect, about 2 times n comparisons, which is better than n log n. So selection can be performed faster than sorting. That's the moral of the story. And selection is an important problem for many purposes. For example, if you want to estimate quantiles in a distribution of scores after the SAT exams, the GRE exams, you might want to do selections. So Quickselect is faster than quicksort. Quickselect is still randomized. It turns out that there's also a deterministic algorithm for selection which takes order n time, but that is rather more complicated, and we will not cover that in this course.